Hi there, I spotted this strange thing on eBay and it looked as if it might still be useful as a load resistor. Buying such a vintage thing in unknown condition is always a gamble, but I made an offer and I got it. A few days later, this thing arrived. Obviously somebody had fun painting it. It has roughly the dimension of a toaster and the visible coils inside make it even more toaster-like, but of course there's no slot for bread. On one of the sides is a scale of sorts and a number of holes into which a thumb screw can be inserted. The other sides have nothing remarkable. It's an all-metal construction and surprisingly heavy. But there is a label and a line cord emerging on one of the small sides. The line cord looks ancient with an outer cloth insulation, probably for heat resistance. It's quite dirty but otherwise still in good shape. Any plug it may have had has been cut off. The label states that this was made by the Curtis Manufacturing Company in London, England. It is rated for 250/110 volts and 500 watts. I tried to find this company, but that was not helped by the many companies with the same name. What I have found is that the UK Science Museum Group holds an old rheostat in its inventory made by this company and dated 1901 to 1930. The eBay listing mentioned that it might have been part of a film projector. The only way to get in appears to be the bottom plate, which is held by its 3 feet. And once they are gone, the plate can be lifted off. It's pretty rusty on the inside, but the rest of the unit looks surprisingly clean. Each side holds a set of porcelain holders which support a resistor coil. The top one is apparently just one large resistor, while the bottom one has tabs to go to the holes for the thumb screw. The wiring is actually pretty straightforward. The upper resistor is connected to the red wire of the line cord and can be completely bypassed through the diagonal wire. The black wire goes to a terminal which is connected to the metal plate with the thumb screw holes. So by inserting the thumb screw into one of the holes and tightening it, its tip will eventually make contact with one of the resistor tabs, thus completing the circuit. I found a mark scratched on the inside. It reads RL69. RL may be the person who assembled it, or maybe the last service. It feels older than 1969, and maybe this was the date when the line cord was replaced, because everything else looks very original. The legend on the outside shows 110 volts on the left and then 200 to 250 volts in steps of 10 volts with 250 on the most right. Obviously this unit was used as a series resistor connecting a 110 volt device to a mains voltage selectable between 200 to 250 volts by converting the surplus into heat. But something is seriously wrong here. The writing on the legend is actually upside down. Remember, the feet of the unit are on top in this view, so we are seeing this unit upside down, but the legend is readable. Compared with the wiring, it is clear that 110 volts should be on the right, not left. Inserting a thumb screw there bypasses all resistors, directly connecting the red to the black wire. I suspect whoever was painting this removed and later accidentally installed the legend upside down. Imagine the fun if this unit was set to 250 volts and then the 110 volts device was plugged into mains without any resistor in series. Anyway, what resistor values are actually in this unit? Let's find out. That long resistor without tabs is about 15 ohms. And the one with tabs measures about 16.5 ohms in total. The contacts are a bit corroded and not easy to probe. About 2.3 ohms on the most left, and it turns out that all the tabs are roughly between 2 and 3 ohms, pending a more accurate measurement. The most right tab shows 19.5 because, thanks to the diagonal wire, that part of the lower resistor is actually in series with the 15 ohms on the upper resistor, and something like 4 ohms. Here's the schematic. I measured the resistance values a bit more carefully, and this is basically what we have. Depending on where the thumb screw is inserted, shown here as the arrow on the bottom, one of the tabs is selected, resulting in a specific series resistance in line with the 110 volt device. If the most right position is selected, the whole resistor arrangement is bypassed and the device is directly connected to mains. Let's do some calculations. For example, if a mains voltage of 200 volts is selected, the series resistor is 18.9 ohms. Since the connected device uses 110 volts, the remaining voltage across the series resistor is 90 volts. With 18.9 ohms, this means a current of 4.8 amps flows and a massive 429 watts would be converted to heat, just inside the 500 watt rating. This is truly a toaster, so I decided to call this unit my Curtis toaster. For 200 volts everything's fine, but for 220 volts and above, the same calculation reveals that the 500 watt rating would be exceeded. At 250 volts, a whopping 658 watts would need to be dissipated. Maybe the 110 volts consumer did not draw that much current. This is where the last three columns on the right come in. I calculated the maximum current that could flow through my Curtis toaster to stay within the 500 watt rating. But a reduced current results in less of a voltage drop across the series resistance, which means that the consumer will sometimes get a bit less and sometimes a bit more than 110 volts. For example, at 240 volts, the device would get 118 volts instead of 110, but that would probably fall into the acceptable tolerances. So far, this is about the original purpose of this device, to allow a 110 volt device to run at higher mains voltages, but I will be using this just as a selectable load resistor. It would be wrong to assume that each part of this resistor is capable of handling 500 watts. This unit as a whole is rated for that, but to do this, each resistor has only to handle a part of 500 watts in proportion to its resistance. This is shown in the last table. When using a conservative load of 4.1 amps, which corresponds to 250 volts when all resistors are in play in the original use, each resistor only dissipates the values you see here. These are definitely safe values, but since Curtis made all resistors out of the same material, I assume I can exceed this by a relatively large margin, probably double the watt value of the smaller resistors. After all this theory, it's time to start the conversion of this unit as a selectable load. As a start, I removed the line cord, as my plan is to add binding posts for all the resistor tabs. I also decided to keep the thumb screw arrangement and instead mount my binding posts on the opposite side. Since I need to use blank wire because of the heat, a cutout in the housing provides the space to access the resistors. A cutting disc on an angle grinder was helpful in doing this surgery. The binding posts are all on one strip of aluminum profile, which will be mounted using standoffs to avoid touching the enclosure. Again, this is a precaution to avoid melting the plastic in the binding posts when this toaster gets hot. The resistance on the red binding post is determined by whatever has been selected using the thumb screw. The easiest way to connect this binding post is reusing the terminal where the black lead was previously connected, which already has the connection to the thumb screw bus bar. I tried soldering on the existing wire connecting the 15 ohms to the 3.9 ohm resistor, but it did not work. Although these are copper wires, they are so tarnished that even flux would not help. Anyway, since soldering would not work with the other resistor tabs, I used the method that works for all, which is undoing the nuts and adding my new wires that way. On the tabs for the thumb screw, the resistance wire is always held between two nuts. Luckily, this allows me to move the left one further inwards to make room for my new wire. I used pliers here to tighten the nuts, but this is not a good method, and once I found a suitable spanner in my collection of metric and non-metric tools, I only used the spanners. Once my new blank 1mm copper wire was attached to the tab point, I soldered the other end to the binding post. A quick test to see if everything is working so far. The bottommost binding post is the common one, which makes use of the existing diagonal wire to get to the beginning of the resistance chain. From there to the next binding post, I have the expected 15 or so ohms. And from the common to the red binding post, I have 15 ohms plus whatever tab has been selected by the thumb screw, at the moment 21.2 ohms in total. If I rearrange the meter for a moment, you can see that the resistance goes infinite when I undo the thumb screw and is restored when I put it back in. As all this is working, I proceed to connect the rest of the binding posts in the same way. Here's an example. Using the spanner to loosen the nut of the next connection point, removing the nut and the washer, and then loosen the second nut to move it further inwards to make space for my additional wire. Then of course putting it back together. Here's the unit all wired up. Although it doesn't look that way from this perspective, there's plenty of clearance between my new wires running vertically and the original wiring underneath. From the common binding post on the left, we have 15 or so ohms to the next one, and then 19.1, followed by increments of roughly 2.2 ohms at each binding post. Last job, apart from closing the unit, is to turn the latch in the right way up. It's just held with 2 screws and reversing is no problem. As a first test, I use the 15 ohm setting. Eventually I will print out a legend with the ohm values and glue it on the aluminum bar. I set the power supply to 30 volts, sorry that the numbers are a bit hard to read on camera, it's much clearer when looked at directly. Anyway, we have almost 2 amps, which makes sense, 30 volts divided by 15 ohms. There is of course some loss in the connection cables, but the dissipation should be about 60 watts. And a quick look through a thermal imaging camera confirms that the 15 ohm resistor is moderately hot, about 71 degrees Celsius or 160 degrees Fahrenheit. Let's try a lower resistance, 10.5 ohm instead. And now we have nearly 90 watts dissipation. The thermal imaging camera shows that a section of the far side resistor is now very hot. There is still some residual heat on the near side resistor which is slowly cooling down. Let me turn the unit around. Nearly 140 degrees Celsius or 284 degrees Fahrenheit. And while I can still touch the enclosure briefly, I would not want to keep my hands on this any longer. My new addition to the lab, the Curtis toaster resistor. I'm quite happy how well this eBay gamble turned out in the end. If you enjoyed my videos, don't forget to like and subscribe. There are many more projects, repairs and reviews coming up, and it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.